Item B, intrinsic geometry, exterior algebra in 3 dimensions. Now could be 2-dimensional, 4-dimensional, and so on. Now B part 2, manifold, push forward and pull back. B part 2, lecture 4, adjoint operator. You see, adjoint operator is fundamental for in this case, okay, to map from one manifold to another manifold a vector. Okay, that's a very, very crucial tool for this operation. Now, consider A and B the space where L is the linear map. L map A to B. Now, the transpose of L transpose, maps back B to A. See? This is the space. I'm considering only a 2x2 vector, 2x2 elements. So, A, okay, the space A, there's a vector V, this is L, the linear map, in this case, this is L applied to V, this is also a vector. Now, this is U, you see, the L transpose, okay, applied to U is mapped from B to A, you see. Now, what is, in this case, the vector A belongs to space A, and vector U belongs to the space B, as is shown on this figure. Now, by inspection, the inner product of V with this vector over here, okay, the mapped, this is a mapped vector U, okay, in this vector space A, you see? Now this is identical, this is equal to the inner product of U times the map from A to B of LV. You see? That is clear on this figure over here. Now, let's present a numerical example, okay, just for you to test this equality over here. Now, given L, that's simple, 1, 2, 3, 4, okay, then LT, L transpose, this column here is the first row, the second column in this case, 2, 4, this 3, 4, and 3, 4 is the second row over there, this case. This row, this column. This first row, first column, second row, second column. That's L transpose. Now, let's consider V with 1, 3 components and U 2, 1 components as an example, numerical example. Let's calculate, okay, LT of applied to U. So LT is 1, 3, 2, 4, just copy from here to here, and there's a vector U. A vector U in this case is 2, 1, 2, 1. So if I multiply this square matrix by this row vector, 2, 1, this leads to the vector 5, 8. Likewise, LV, you see, LV over here, you see, is 1, 2, 3, 4. That's a matrix A in A, L. And V is a vector also that belongs to A, okay? And LV belongs to B. You see here and you see there, okay? That's quite easy. So if I multiply this 2 by 2 matrix by this 2 by 1 vector, this is 2 by 1, the result, LV. Now, let's calculate, okay, the right-hand side here first. Doesn't matter. So the inner product between U and LV, okay, ULV. You just, attention, just copy from here to there. You see, there is no problem. This is a vector, okay? 2 by 1, this is 1 by 2. So this is a scalar, okay? This here is scalar. This is scalar. Likewise, the same, the inner product between V and LT of U, just the left-hand side, on this, this equality here, this will be the same result. You just copy V13, LT of U is 5, 8. You multiply this 1 by 2 matrix, this is 1, this is 1 by 2, this is 2 by 1, this is 1 by 2, this is 2 by 1. So this is also the same scalar. So this numerical example, okay, shows clearly that this operation over here, it works, they call adjoint operator. Okay, thus, you see, you can lead to this equality over here. This example, you see, now the next lecture will be applied to the two manifolds, okay, M and N. And I use the adjoint operator just as we presented over here, okay? So lecture 5, we apply the adjoint operator just using these tools, that's important tools in this case, in the intrinsic geometry. And also in the extrinsic geometry, okay, we can use in linear algebra, okay, the adjoint operator. That's as this, okay?